problems on more transformations. The one small theorem, there will be problems. If T is 1 1 and U1 U2 up to UN are Li vectors U, then T of U1, T of U2 up to T of UN are also Li. U1, U2 are Li. T of U1, T of U2 also Li. Li, LD about the Li and LD and T transformations. So if T is a 1 1 mapping, you know by definition, and U1, U2 up to UN are Li vectors, okay? Li, multiple 0. Then T of this will be, I want to take Li. Li already, you know, technique is consider alpha into alpha 1 into T of U1, alpha 2 into T of U2, alpha n into T of UN equal to 0. Now T is a linear, of course T is a linear transformation, no doubt. So alpha inside, alpha 1 U1, alpha 2 U2, alpha n. Now 0 is, we know T of 0 is 0. Again T is linear, alpha 1 U1 plus alpha 2 U2 plus alpha n UN. So T of this equal to T of this, and T is a 1 1. Therefore what? Okay, alpha 1 U1, alpha 2 U2. In this way, alpha n UN will be 0. Reason T is a 1 1 mapping. Now, as of Li said, U1, U2 up to UN are Li vectors. Therefore, they are multiple 0. Each scalar multiple 0. Alpha 1 0, alpha 2 0, alpha 3 0, alpha n 0. Each 0. So that is your n. Consider alpha into vectors, and lastly show, okay, they are zeros, scalars. Therefore, these vectors T of U1, T of U2, in this way T of UN are also Li. So use Li, T of E is also Li. Next, okay, big example, 6 mark question. Prove that a linear map T from V3 to V3 defined by this way. So T of E1 is E1 minus E2. T of E2, 2E2 plus E3, T of E3, E1 plus E2 plus E3. Is neither 1 1 nor onto, both. Neither 1 1 1 is T equal to 0, just like the theorem, onto range equals to dimension of V, same. Solution. So T T is a mapping from V3 to V3 defined by T of E1, E1 minus E2, T of E2 to E2 plus E3, T of E3, E1 plus E2 plus E3, where E1 means 100 standard basis, E2 means 010 standard basis, E3 means 001 are standard basis of V3. Okay. That means T of E1 will be E1 minus E2, 100 minus 010 will be what? 1 minus 1, 1, 0 minus 1, minus 1 and then 0. So T of E2 will be, okay, 2 E2 plus E3. So 0, E2 double, 2 and E3 1. And T of E3 is E1 plus E2 plus E3 means 1, 1, 1. So this is known to us. Now comes to 1, 1. Okay. 1, 1, NT equal to 0. I want to show. So NT, you know NT, U belongs to U such that T of U equal to 0. Here V3, three-dimensional vector, U3 vectors. So suppose say X, Y, Z is a one vector of V3 such that T of X, Y, Z will be equals to 0. So take outside the bracket, we simplify in a outside the bracket. So T of X, Y, Z, but your T in terms of E1 into E3, not in terms of X, Y, Z. So this is written as X into E1 plus Y into E2 plus Z into E3 because standard basis. You know, that's why X into E1, Y into E2 plus. If you add this one, we get. Now X linear, T linear, X outside, T of E1, Y outside, T of E2, Z outside, T of E3. So X outside, T of E1, okay, is like 1 minus 1, 0. T of E2, 0 to 1. T of E3, okay, simplify. X, 0, Z minus X, 2Y, Z, 0, Y and Z equal to 0, equal to 0, equal to 0, equal to 0. So that means, okay, X plus Z equal to 0 minus X plus 2Y plus Z equal to 0, Y plus Z equal to 0. Okay. So from this X is minus Z and from last Y is minus Z. Z is 0. Okay, not solve. Okay, do not solve the equation, 3 equation. Okay, so therefore this NT, three-dimensional vectors X, Y, Z. So X is minus Z, Y is minus Z and Z is Z. This is minus Z common, 1, 1, minus 1. Or it is a span of single vector. Okay, span of a single vector. So span alpha into beta into, so manage it as a scalar constant. Okay, multiple. So the single NT is a 1. Okay, so not 0. That means NT is not equal to 0 vector. This contains single vector, is a non-zero. Therefore, T is not 1, 1. T is not 1, 1. When 1, 1, NT is 0. Yesterday we have the point. Now RT, 1, 2 depend on the RT. So what is RT? Okay, T of U's. So that U belongs to U by definition. Here T of U, so T of X, Y, Z. so that this xyz is a vector of V3, three-dimensional vectors. Or this okay, T of U's. So three bases are okay, U1, U2. So T of U1, T of U2, and T of U3. By the theorem, by this definition, span of. Again, yesterday theorem 4 point. Okay. So what is the range? This is by definition. This is by the definition. Okay. I want by the theorem. RT is a span of T of E1, T of E2, T of E3. E1, E2 are the bases. Okay. So here not E1 is T of E1, T of E2. Bases are given. E1, E2, E3 are the standard bases. So T of E1, T of E2, T of E3. So T of E1, 1 minus 1, 0, 0, 2, 1, 1, 1, 1. It's like okay. Now you know span contains Li vectors, must be Li, then we can say rank. Who can confirm. So Li really now check. Determine technique. Li or LD equal to 0, LD not equal to 0, Li. So 1 into 2 into 1 minus 1 minus and minus 1 into 0 minus 1, 0 into 0. So 2 minus 1, 2 minus 1, 1, 1 into 1, 1, minus minus plus and plus again minus equal to 0. So equal to 0, LD. Vectors are LD. Then what happens? So neglect one vector from this three collection. Always remove last one. Now remaining only two vectors. 1 minus 1, 0, and this. This of course Li, yes, alpha into beta into equal to 0. You can simplify and 0. So the RT will be now 2. So dimension of RT will be 2. Dimension is number of vectors, 1 and 2 vectors. Okay, but dimension of right side V3 is 3. So dimension of RT is 2, dimension of V3 is 3. Okay, not equal, not match. Dimension of RT is not equal to dimension of V3. Okay, V3 codomain space. This must be matched because they are rank in the right side set. Codomain is called as codomain. Okay, therefore RT cannot be equals to V. RT range is cannot be equals to V, equal to V. That means again not R2. So T is not onto also. So not 1 1 and not onto both. Okay. So for 1 1 NT equal to 0. You have to show. And for RT onto RT must be equals to V. Again example on this 1 1 onto. So let T is a mapping from V2 to V3. Be a linear map defined by this T of x1 x2 equals to x1 minus x2, x2 minus x1 and minus x1. The question is show T is 1 1. 2 more question. very small. 2 mark question. Solution. So let T is a mapping from V2 to V3, be a linear mapping and defined by in this manner. T of x1 x2 is x1 minus x2, x2 minus x1 and minus x1. Okay. So you have to show T is 1 1 1 1 means what? Nt equal to 0. We have to show Nt null space. Okay, must be equals to 0. Means U belongs to U such that T of U equal to 0 by definition. So here U means this U space, 2-dimensional space. Suppose say x1 x2 2-dimensional vector of V2 such that T of this will be equal to 0. So take separate. We cannot solve in the bracket. Equations are separate. So T of this equals to 0, but T of this is given to you. x1 minus x2, x2 minus x1 and minus x1 equal to 0. 0 means 0 0 0 vector. Compare x1 minus x2 equal to 0, x2 minus x1 equals to 0 and last minus x1 equals to 0 means from the last x1 equal to 0 we get x1 equals to 0, x2 equals to put here, okay, put in 1 suppose, well we get x2 also 0, so both are 0 here now. Nt means we assume x1 x2 vector, 2-dimensional vector, so x1 is 0, x2 is 0, both are 0. So Nt is x1 is 0, x2 is 0, that means 0 vector. So Nt equal to 0, null space, that's 1 1. So P is 1 1. So this confirm. Nt equals to 0. Again example, let T is a mapping from V3 to V3, be a linear defined by this like. So T of x1 x2 x3 equals to x1 x2 same and x3 will be 0. Question is now find range and kernel both T. Solution. So T derivative in the mapping defined by this line. So first range and kernels. What is range? See by definition range of T, that means RT is a by okay definition T of U's such that U belongs to U. So U means here V3, 3-dimensional vector, okay, x1 x2 x3 such that T of x1 x2 x3 is equals to 0. Sorry, T of U, T of U means T of 3-dimensional vector x1 x2 x3 only, that is given to you. Okay, it's x1 x2 and 0 3-dimensional vector. So here basis is not given, so RT is a by theorem. RT is a T of E1, T of E2, T of E3, E1, E2 are the basis. If basis known to us, then we can use that technique. Here basis don't know, so I have to generalize. So this is same as x1 into 1 0 0 plus x2 into 0 1 0. Okay, x1 x2 0 0 x1 into 1 0 0 x1 into 1 and this 0 x1 into 0 and x2 into 1 this one. Okay, break in terms of this. Okay, so it is a span of 1 0 0 and 0 1 0. In your span of vectors are RT is a span of T of E1 E2 E3. So here two vectors, span of two vectors, span of three vectors. So this is the simple adjustment. Simple, this is define is simple. That's why I make here simple adjustment. So this RT is sufficient. Branch, kernel, kernel of T, then T. By definition, U belongs to U such that T of U equal to 0. Okay. By definition. So U here vector, again 3-dimensional vector x1, x2, x3 such that T of x1, x2, x3 equals to 0. So separate or here also continue x1, x2, x3 so that T of E1, E2, E3 is this like x1, x2 and 0. Yes, x3 will be 0, third will be 0, x1 same, x1 same, x2 same, x3 will be 0. T of this equals to 0. So 0 means 0 0 0. So x1 equal to 0 equation, x2 equal to 0 and s3, about s3 don't know. So x1 equal to 0, x2 equal to 0, about the s3 don't know, because 0 equal to 0, no conclusion. So we can say only x1 vector is 0, x2 equal to 0. We solve this separately. Okay, so a single vector now, s3 is common. 0 0 1 means span of single vector 0 0 1. This multiple, s3 is a scalar multiple. Okay, alpha into beta into gamma into, this is a multiple alpha into vector, therefore span. So this is like NT contains single vector, span of 0 0 1. Okay.